time. This one is the potential of the biomass. The Jatopa oil, I have the one. Okay, you see, we use the seed extract the oil, then it left over the Jatopa biomass. So we convert the Jatopa biomass into the carbon-based acid catalyst to be used back in the esterification process and also the acid process. Yeah, because we converted into the acid-based catalyst, which suitable to be used as the acid esterification process, then followed by the biodiesel process. So this is what I want to show you. So in this study, we want to investigate the preparation of the carbon acid catalyst from the Jatopa, the oil silicate. Jatopa, the oil silicate, which the Jatopa biomass that we already extracted the oil. Then to analyze the characteristics of the prepared carbon acid catalyst. Then last one to study the effectiveness of the carbon acid catalyst in the biodiesel production, which we use back in our biodiesel production. So this is the methodology. You see, for the first one, we just dry up to 24 hours. Then we do the carbonization at the appropriate temperature determined by the TGA for 4 hours. Then we sulfone it with the sulfuric acid at 90 degrees for the duration from 5 to 20 hours under the constant stirring condition. Then after we prepare the catalyst, we need to do a series of the characteristics. So any one of you are working on the catalyst? No. Any one of you? No. Yeah. If you want to develop or design a certain catalyst, there are a series of the characterizations we need to go through. For example, the SEN, the BT, the EXT. This one is a series of the characteristics I need to go through to make sure the catalyst that we produce is the desired catalyst here. So lastly, we study the reaction study, which we use the catalyst in our process. Then lastly, we see the reusability of the catalyst. Reusability. So the catalyst reusability to see whether it can be used up to how many cycles before it's reaching. So this is the result. So this is the TGA analysis of the Jatopa oil seed. So yeah, as usual, we know for those conduct the TGA, we know that the first 100 to 120 degrees is what the loss of the waters. Then another one is what is indicate the degradation curve between this one is 350 to 450. You see, degradation happens. So with this, we choose 350 degrees C, only the partially carbonized of the silicate. Because why? We don't want to break down the micro molecule and remove the organic portion. We don't want that happen. So we only calcinate at around 350 degrees C. We don't want to break structures for that catalyst. So this is how we do the sulfurification at 5 to 20 hours. But after we conduct, we found that the total acid content already reached its optimal condition at around 5 hours. So we just use 5 hours, which the total acid can be reached up to 2.24 more per gram. So there are no any significant increase in acidity. So that's why we do the carbonization at 350 C and also the sulfurification at 5 hours. So this is the SEN image of activated carbon which is the acid catalyst. We plan to use the acid catalyst. So the pore volume is around 2.6 mm square. Then the pore diameter is 6.77 millimeter. Both same for the carbon and also the catalyst.
So
yes.
There is a decrease in the surface area of the carbon compared to catalyst.
Decrease with the decrease in the surface area.
Because the carbon has more surface area compared to catalyst.
Correct.
What could be the reason for this?
Yeah, why? Decrease in the surface area, right? Yeah, this one decrease in surface area. The pore size is
Pore size is decreased, but
almost similar.
pore volume is decreasing.
Yeah. This one we need to check why
Maybe the catalyst is loaded with some.
How is the catalyst situation?
yeah we
Generally, activated carbon will have greater surface area.
yes. This one with the activator, this one we put in the acid. Yeah. We put in with the acid. So the total surface area is just 1.92 millimeter square per gram compared to the just the carbon. I mean this one is from and also the pore volume is around almost similar. I can say 3.6 and 3.22 millimeters and cube per gram. Then we have the acids around 2.25 because we want to convert it into the acid catalyst. Acid catalyst.
Sir, which catalyst you use? Which is the catalyst you use?
This one is the what? Our own jatopa oil.
Catalyst.
Yeah. Our own. We convert our on this one the own jatopa seed after extract. Yeah. This one. We carbonize at 350 degrees C to convert it into the catalyst to develop the own catalyst. Then this one is the functional group. It's not very okay. Then after that we do the reference study. We found that by using our own prepare catalyst, it found that it also effectively can be convert the biodiesel up to the conversion yield of close to 100%, which is 99% at 7.5 of the catalyst ruling, with the methanol ratio around 12 to 1, which almost 99%. Then this one, the temperature we are using is around 60 degrees C, which is quite common for the biodiesel conversion, which the 60 degree is the optimum. So it means by using our own catalyst is also able to achieve the similar result. Then the conversion yield for the reaction time is around 1 hour. It's also same. It's also similar by using our catalyst. However, when we do the reusability, so after we use the first cycle, it can reach up to 99% based on the previous result. But after the second cycle, it's only the conversion here is only 96% and 90%, 81%. So we would recommend, because after the fourth cycle it's reduced more than 10%, more than 10% of the, you see here 90 around 10% of the year. So we recommend to have the possible to regeneration of the sulfurification process of our catalyst.
Is
So the good thing is to use this solid catalyst compared to the liquid catalyst. Is what the solid catalyst can be reused, then easy to separate. Because currently industry are using the liquid acid catalyst. So that's the thing. But the thing is, after the third cycle, we need to reactivate catalyst. So this is the this is the second step. This is not so important already, because after that we just prove that the acid the biodiesel that we produce are also almost similar with what we produce by using the conversion process and conversion catalyst. So this is the conclusion. This can recommend to use up to four cycle, but I would recommend use up to 3 cycle. Then we can be activated, and the biodiesel here can be achieved up to 96%. Is almost similar. Then the biodiesel that we produce also fulfill the STM and EN standard at 6.1 or 12.1 methanol to oil. 6 to 1 the one is 12 to 1, right? I don't remember. 6 to 1 is not the highest, should be 12.1, I think. I think it should be 12. 12. Normally it's 12. It's not 6. It's 12 to 1. Should be 12 to 1. 12 to 1, you see here. No. It might be 6. This one is the second step already. Let me see. 6 to 1. Because 6 to 1. This one is the second stage. It's a triacidification. 6 to 1. 6 to 1. This second step, not the first step. Second step. 6 to 1 is correct. 12 to 1 is the first stage, is the acid acidification. Yes. Correct. These are 6 to 1. Correct. This one is 12 to 1. Yep. So from this study, we found that the two findings. The jatopa, the oil, can be converted into the acid catalyst, which is better for the process. Why? Because the catalyst can be separated easily, then can be reused back. Yeah, that's the thing. Yep. Any questions? Any questions? Yeah. If not, I think today we just end here. Because, yeah. This one, heterogeneous catalyst. Heterogeneous catalyst, so that the benefit for the heterogeneous catalyst is what? Easy for separation. Easy for separation. And this one is we can develop our own homogeneous catalyst, which is quite stable for the process. Why I say stable? Because you see, we are carbonized at 350 degrees C. That means what? It will not transform or change the phase up to the 300 degrees C, and we use our catalyst at around 60 degrees C only, because the reaction for the acidification is around 60 degrees C. It's quite stable. It's quite stable and sufficient to be used as a catalyst in that process. They're quite easy and simple, because for the acid catalyst acidification process, we just need to put in the acidic into the process only as it.
So how does the efficiency of this synthesized catalyst compare with what is available in the market? I mean, is it comparable or?
No, this catalyst compared to what?
Whatever is available in the market. No.
Okay. No, we put it that way. Of course, the current commercial catalyst is still better. If we are talking about the homogeneous catalyst. Homogeneous catalyst is still better. Of course, I mean by the industry process still better, but it cannot be recovered. Some of the process we need to recover, because some of the process why we need to recover, they need to get the pure products. That one can be recovered easily.
So because it is heterogeneous, it becomes easier. And in
yes.
the long term, it will be more useful. useful.
Correct. This one thing. Then second thing, reduce the overall cost. Overall cost, that means we need it. Because it can recover. That one. If even though for the homogeneous catalyst you don't want to recover, you just keep putting. Yeah.
What is the importance of keeping this catalyst acidic?
Just keep at the normal condition because it's not transformed or whatever at the room temperature. It's quite stable. For the solid it's quite stable because we activated up to the 350 degrees C. That means at the room temperature is already quite stable. Quite stable. Then we sulfurication, make the sulfurication at around 90 degrees C. So as long as it's not heat up to the 80 to 90 degrees C, I think it's quite stable. Yeah, at the room temperature. I mean at the room temperature. Yeah.
Sir, I have from your previous session.
Hmm.
Like, once the biogas is used as a bioadsorbent for the removal of any organic pollutants, so after multiple reutilizations, there will be a point where we cannot use it again.
Yes,
Right?
correct.
So regeneration is not possible. So what is your view on like applications of the spent biogas? What to do with that, except for landfill?
Yeah, that is the thing that facing by not only as a bioabsorbent, it at many other purpose. You see our water filter and all these things. How we going to recycle? So this is what we need to think. So how you see if that absorbent to absorb something that useful, we can recover. Heavy metal can recover. If we use the biochar to example only to absorb the heavy metal. Then from that we can find a way to extract out the heavy metal. Then for other purpose. Then for the dye, I don't know what is the purpose yet. What we going to use yet. Similarly, you see now people is looking for the what material to store the hydrocarbons. I ask them, they can put in how they extract the hydrogen out. They can keep storing. Similarly, they do the carbon capture materials. They just put in the carbon, store there. It's not solve the problem. Then if you want to use, how to restore back?
But so we can't use the spent one, no? Once we have to store carbon, we generally use it as soil sequestration into the soil. And if we use, as he said, beyond a point, this thing cannot be reused. Like 5 or 6
Correct,
people, it will be reused. After
correct.
that,
That's okay.
whatever we are putting in will stay in there. But we
Correct.
can't use it again for soil sequestration. That
Correct.
is, as he said, a very genuine problem, an emerging
Yes,
problem.
correct. This I tell you. So that's what I pointed out. More and more similar problem that you mentioned. More and more problem because carbon capture is a very hot topic. But only the carbon capture for me, for my point of view, and for many scientists around the world, especially you know the what professor, what's the name already? The editor of the RSER, he mentioned one thing. He do the analysis of all the potential potential green technology. We found that the carbon capture really cannot help the world because we just keep storing. But the carbon capture with the future emission, how we going to use it? Because we just store it, but for what and how?
Sir, I have a question.
Yes.
So, you have nicely explained that how sulfonation plays a major role while preparing our catalyst. So, my question is that in most of the Indian situation, Indian coal is high in sulfur content. So, but that is not useful in our steel industry or like other purposes. So mostly before using coal, what we do, that is we go for coal washing to make it
Less
ensure
sulfur.
the desulfurization.
Desulfurization.
So
Yes.
up to what extent this coal washing or coal desulfurization should be taken place if, if our aim is to use the coal itself as a catalyst.
Yeah. Oh, you want to use the coal as a catalyst or what?
Yeah. Coal, if we want to use it as a catalyst, like it's already inbuilt content with sulfur.
I know, yeah.
So this, but the thing is that up to which extent it should be desulfurized. Means from I'm talking. I just want to know the reverse process. Now from raw biochar, you are adding H2SO4 like for 5 hours, 10 hours, or certain time with certain concentration to make it sulfonated. My motto is to know that is how we can go for and what extent we need to do the desulfonation of available coal sample so that we can use it as a catalyst, be it in hydrothermal torrefaction, liquefaction, or in pyrolysis.
Yeah, that one also, yeah. That's why it depends on the application. So that's why, if possible, should be make it a no sulfur. If possible. But you see, if you want to use as a pyrolysis process that is burn until very high temperature, the sulfur might be released, right? Not released. So until which stage is really depend on you. What type of what is the quality of the catalyst that you want to produce? I can give you one example. The biogas. Normally, the biogas from what already? Biogas. Yeah, correct. They contain a lot of the sulfur. Sulfur by produced. So before they use the biogas, they do the desulfurization to correct the sulfur because sulfur is very useful product, right? Now, if we able to recover back the sulfur, sulfur is useful in the many industries applications. So we need to do the desulfurization before we use the biogas. If not, it will harmful to the environment. That is the thing. So how much you want to do the desulfurization, it really depends on the process and what you want. What is the standard that in your country or in your region?
Mountain cake based biogas must be having
Correct. That's the thing. We need to do the desulfurization. So it really depends on you. What is the regulation is law of your country? But ideal case should be no. I mean, cannot be no. Ideal case should be no. So we try to desulfur as much as possible. As much as possible. Because if not, in many green energies, green energy, it will release the sulfur even though the hydro energy, the hydro energy around the hydro energy contain a lot of sulfur. If you have chance to visit any hydropower plant, you can see surrounding area all is yellow color, yellow color sulfur. Sulfur release, yeah, sulfur is why release because you see the hydro water go down to the land, and the sulfur from the ground release. That's the thing. Leaching. Leaching, yeah.
leaching from the soil.
Soil. Yes. Soil because the